All right. How you guys doing? Ready for finals? Just about, almost. All right. So this last class for us. This last class for any of you, or you got some more after this? Okay. Almost there. Last one. Gonna skip that one. Gotcha. Yeah. All right. Well, let's get to it. Before I launch into the homework solutions, I'll just say that you can expect the exam to be rather similar to the previous ones. We have a little extra time, so there's probably going to be a little bit longer. Not that I'm like trying to make sure every last minute's used, but it'll just be scoped a little bit, like maybe one more problem, kind of a thing. So essentially, you can expect about a problem or two small problems from each of the first two exams, and then about two problems or maybe like three small problems or something like that from the remaining section with the activated sludge stuff, the BOD, wastewater treatment. So that's kind of the plan. As you probably have felt throughout the semester, this is cumulative in the sense of we learned about rates and we've been using rates for like almost every subsection of our course and mass balances and all that. So it'll be cumulative in two senses, 50% just in terms of touching back on the old content and 50% of the more recent stuff, but it also kind of draws on all the principles we've learned. So that's the plan. I think I probably need to get the participation scores sorted and everything. I'll try to have that done kind of by mid next week, maybe late next week. If you've been keeping up with the quizzes online, chances are you're doing great. And those of you who are here, I know that you are often here, and that'll do nothing but good for you also. Okay, so with that, let's take a look at homework 4 so you can kind of see what's going on. Ask me any questions you've got. If it sparks something else, please speak up if you want to know about something else. All right, so the first problem, we have a wastewater treatment plant using activated sludge for secondary treatment. We've got a flow rate there of primary effluent, and remember primary effluent, that should mean that we are coming out of some primary sedimentation. So primary effluent is what's coming into our treatment where we're going to have some activated sludge, then into a secondary clarifier. And as the problem will show, I think we're going to be recycling. So our typical system will then have a recycle line like that. Okay, so the mixed liquor has a concentration of 2,500 milligrams VSS per liter and a return activated sludge concentration of 10,000 milligrams VSS per liter. So we could go ahead and label a couple things. This is the X recycle. That's the 10,000 milligrams VSS per liter. The X in here, that's the mixed liquor concentration, so to speak. And we're given that X is 2,500 milligrams VSS per liter. The substrate concentration in the primary effluent, that means the influent for this system, that's S naught, is 220 milligrams BOD per liter. We have an F to M ratio given at 0.52 milligrams BOD per milligram VSS per day. And the cell retention time, theta C, is 9 days. Okay, just so I have it all written. Oops, yeah. Okay, so we can write it all that way. And the first question says, what is the volume of this aeration tank? So given all that, we need to have some way to find the volume. Now, we're given a flow rate, we're given several parameters, and so as we think about how to get to the volume, we might be thinking of something like, well, do we have the residence time? We don't have the residence time per se, but we do have the cell residence time, so maybe we can possibly use that. Or perhaps this food to mass ratio, because we'll need the volume in that one as well. So let's also go ahead and make a note that the flow rate itself, that was given at 0.35 cubic meters per second. Okay, so we want to know volume. We know that if we had the theta, we could say, just say theta equals V over Q. The theta C is not quite so simple, and we need, we might use that. We could say, we could check and say, well, let's see if we have the information. Theta C is Vx divided by theta C, excuse me, QW XW. And here we might notice, well, we don't have any information about how much waste flow is going out. We don't know QW. So even though we kind of know XW, because it should be the same as XR, we don't know QW, so we can't really use that. So then we can take a look at the food mass ratio formula. That one is Q times S naught divided by, divided by Vx. So this one, we have all those pieces, so we can actually rearrange this and solve for V. And remember, we're not splitting apart the food slash mass. That's just one combined unit that we're going to deal with. So we're going to move volume to the other side and say this is going to be equal to Q S naught divided by S slash M times X. And fortunately, we have each piece of that. Now we do have to probably convert Q into days. So this would be the 0.35 cubic meters per second times, there are 86,400 seconds per day. And then put it into our equation. I didn't have that written out for you here, but you can imagine that's a lot larger. It's going to, if we take 86,000 into a third, that's about what we'll get, somewhere around there. So somewhere around 28,000 cubic meters per day or something like that. So at any rate, the volume, once we put those numbers in, the volume should come out to be 5,118 cubic meters. Okay. Make sense? All right. So next piece, we are asked what is the waste activated sludge flow rate, QW, right? So here we're looking at if this is our system, we've got the recycle, it's this flow rate right here that we're looking for. Okay, so given that, we had just looked at that theta C a moment ago, the cell retention time, and we said, well, we don't have all that information to use there, but now we do, because now we have the volume. So now this theta C equals Vx over QW XW is a lot more manageable since we solved for the volume. So now we can rearrange and say QW should be Vx divided by theta C times XW. And we have each piece there, but we will have to convert or make sure our units are in the right circumstances. So we can fill this in and say, we'll just start it back up here. Say QW is equal to that 5118 cubic meters. Multiply this by the 2,500 milligrams VSS per liter. Divide all that by our theta C, which was 9 days. We'll leave it in days for the moment, and then our answer is going to be in days. Maybe we'll convert it back to seconds. And multiply this one, that the concentration in the waste should be essentially the same as the concentration in the recycle, that 10,000 milligrams VSS per liter. Because we're not splitting, when we recycle, we're not splitting the concentration here. Okay, so this should be 10,000 milligrams VSS per liter. Okay, so that'll give us, when we put in those numbers, should be 142.2 cubic meters per day. And if we wanted to, we could solve it in cubic meters per second, so it would be a pretty small number, 0.00165. Okay. All right, so then next up we say, what is the flow rate of treated effluent? Now this is, the question here is really getting at how much flow essentially is leaving the plant or leaving the system out the effluent of the secondary clarifier. So QE is what we can call this one. And this is going to be a simple mass balance on, well, where's the flow going, right? So we have the flow coming in that we know. We might stop and pause and think about this recycle flow, but then realize it's kind of outside the bounds of what we actually need or care about, and say, if we draw our control boundary out here, then whatever is coming in and leaving that control boundary is really what matters. So we can say the total flow that we were given, Q, is going to be QW plus QE. So what's going in is equal to what's going out. Very simple. We can rearrange that and say QE then should be Q minus QW. And now it's a little bit handy that I put it into cubic meters per second, because we can simply say that's 0.35 cubic meters per second that's coming in minus that 0.00165 cubic meters per second leaving the waste. And so Q effluent, the treated amount, is 0.348 cubic meters per second. So that makes a lot of sense. Most of our water should be going out the tailpipe. That's by design. Not much of the water is being wasted with this sludge, slurry stuff that we have to extract. It is a volume, it is a flow, but it's not a huge amount. Okay. Make sense? All right. So next up we say, what is the hydraulic residence time for this activated sludge tank? And given that we were just thinking about the flow rates, it could maybe be a little bit confusing. Of course, we know theta should be V over Q. We did solve for V, so that's the 518 cubic meters. The flow rate, we have to think about what's passing through the sludge tank, right? The activated sludge chamber. And really, maybe what I ought to say is in the residence time for water in the secondary treatment as it relates to the biological activity. But the recycle essentially means that there's no net extra flow because some portion is recycled continuously. That's just going to add the same amount of time for the water to stay in there as it was adding flow to change it. So the net flow is what we use, just the regular Q. We don't need to worry about the recycle. It's not affecting this at all. So this just simply becomes 518 divided by 0.35 cubic meters per second. And that's 14,623 seconds, or we can transfer that and get that into days, 0.169 days. All right. Any questions? All right. So next problem, we have incoming wastewater with a BOD5 equal to 200 milligrams per liter. It is then treated in a well-run secondary treatment plant that removes 90% of the BOD. You are to run a 5-day BOD test with a standard 300 milliliter bottle using a mixture of treated sewage and dilution water with no seed, so we're not dealing with the complicated seed stuff, assuming the initial DO is 9.2 milligrams per liter. And so then part A says roughly what maximum volume of treated wastewater should you put in the bottle if you want to have at least 2 milligrams per liter of DO at the end of the test, and you fill the rest of it with the bottle with water. Now, before we move on too far, we have to highlight that the problem is set up telling us we have incoming wastewater. So that means untreated. And this S initial is 200 milligrams per liter of BOD. Now, then we're told that the wastewater is treated. And in the parts A and B, I'm highlighting it's treated, right? What we're dealing with then is treated. So we have to do a small calculation to account for the treatment because we're doing our BOD test on treated water. So we have that 200 milligrams per liter, 90% of that is removed by the treatment. So we can multiply that by 0.1, because there'd be 10% of it remaining, to get our answer, right? We could also say 200 minus 0.9 times 200 would be the same thing. So that means if 10% of 200 is remaining, there's 20 milligrams of BOD per liter remaining in the treated water. And that's what we're going to do our BOD tests on. Okay, so that would be, it's not a particularly complicated concept here. It's just a matter of making sure that you're reading the problem and understanding what you're being asked. Okay, so part A then, we're dealing with that treated water. We put it into a bottle. What's the maximum we could put in there to have at least 2 milligrams per liter of dissolved oxygen at the end if we filled the rest with dilution? So what we're really looking for is in our little bottle, if we think of a little jar, little cap, fill it with the water. We don't know how much can be the dilution and how much can be this volume of wastewater. So that's kind of the question. The most that can be. And we did a problem like this. It was a little simpler the first time we looked at BOD stuff. So we can write up a simple generic equation for BOD. BOD5 should be equal to the dissolved oxygen initial minus the dissolved oxygen final divided by P. Now, P is the volume of wastewater per total, right? So we could just write that as volume of wastewater per 300 milliliters. So by putting that in here, we can look for and solve for this V wastewater. The other thing we can consider is that we know something about the initial and the final. So we need, our initial is 9.2 milligrams per liter, and we need at least 2 as the final. So we can go ahead and put those numbers in and then divide it by this V wastewater over 300. And we know that our BOD that we were actually already know the BOD because we were told it starts at 200 and we removed 90%, so this should be set equal to 20. Okay, so what that means is on the left side here, we could simply multiply the top and the bottom by 300 and then move around the volume of the wastewater to find that value. So we could say volume of the wastewater should be equal to 300 times this 9.2 minus 2, so 7.2 milligrams per liter oxygen divided by the 20 milligrams per liter of BOD. When we solve that, we should end up with a volume of 108 milliliters is V wastewater. Okay, so we can put about a third of the wastewater in the bottle. And if you stop and think a moment about like just the intuition of it, we have a bottle. It starts with 9 milligrams per liter of oxygen, and then we've got some substance that's going to remove oxygen. And that stuff has 20 milligrams per liter of oxygen demand, right? So if our initial dissolved oxygen was 25, we could fill the bottle, right? Because 25 minus 20 gives us 5 remaining. Since it's less than, and it's like 9 is, a little less than half of 20, then we expect that we need to have the dilution by more than 1/2. Then we also have really only 7 milligrams per liter to work with, 7.2. That's our range. And 7 is very close to a third of 20, right? It's a third of 21. So just by intuition, we can say, this number should be something like a third of the bottle would work. And sure enough, that's true for our answer, so it feels like a good check there. Okay, part B says, if we make the mixture of half water and half treated wastewater, what DO do you expect after 5 days? Now, having just elaborated on the intuition, we might be able to see right now, okay, this is, if 50% of it is wastewater, that's probably driving the dissolved oxygen to pretty much 0. So we can do that mathematically, or we can just simply say, probably 0. We'll go with the more rigorous method. So we'll say P is 0.5. That means half of the solution is wastewater, half of it's dilution water. If we want to be very elaborate, we can say that's 150 milliliters for dilution over 300 total, right? Okay, anyway, the BOD5, we know that's 20 milligrams per liter. And we can say we're looking for what is the final. The initial is 9.2 milligrams per liter of oxygen. We don't know the final. That's what we're going to solve for. And we know P is 0.5. And so when we solve that, we will find a negative number. So we'll just do a little bit of algebra. I'm going to skip it and say DO final is negative 0.8. But we can't really have a negative concentration. That does not exist. So we say that kind of takes it to 0 milligrams per liter. Which, again, that also matches our intuition that we talked about. All right, make sense? Any issues? Okay, next up we have a BOD test using 100 milliliters of treated wastewater mixed with 200 milliliters of pure water. The initial DO is 9 milligrams per liter. After 5 days, it is now 3 milligrams per liter. After a long period of time, the DO is 2 milligrams per liter, and it no longer seems to be dropping. And we assume that nitrification has been inhibited, so it's only carbonaceous. That just in case that was relevant in some way. And what this is kind of showing us is we have a 5-day BOD test, and that doesn't really get rid of all of the BOD that could ever be demanded. And so this remaining extra 1 milligram per liter is kind of giving us some indication of what would happen if we left it there for forever. Some ultimate BOD, so to speak. Okay, well, the first problem, what is a 5-day BOD? That's pretty simple. We don't need to do anything fancy here. We'll just recognize that we have our BOD 5 measurement. That's going to be the DO initial minus DO final divided by our dilution ratio, and P, that's 100 over 300. Because it's mixed with 200, that means 100 plus 200 is the 300. So we'll just say that's 1 divided by 3 here, 1/3. All right, so we know the initial and the final. That should be 9 minus 2 over 1/3. That's going to be, excuse me, that was 3, not 2. So that'll be 6 on top, multiply it by 3, and we get 18 milligrams BOD 5 per liter. Okay, part B says, assuming no nitrification stuff, estimate the ultimate carbonaceous BOD. So as a reminder, the ultimate, we described that as L0. We used that when we merged a river with wastewater, and we said, okay, at that juncture, we have some ultimate amount of BOD that would ever be demanded by that stuff in the water, and that's kind of how we described it. That's what we used then for some calculations. That's as if we took BOD with an infinite time experiment. And so the fact that we left it sitting there for a long time and it stopped dropping, that's pretty much what we get. That's our, we can say that's infinite even though it's just, a long time. Okay, so we can say really the simplest way to solve for that is actually the same setup, DO initial minus DO final divided by that dilution factor. And so that's going to be 21 milligrams BOD per liter. Okay. So next up, we are asked what would be the remaining BOD after 5 days have elapsed. So this is kind of a pretty obvious question, but I have it here to kind of get us thinking about that relationship with the ultimate versus the way we run the tests, the 5-day BOD. So it's going to be, this one's quite obvious. We're going to say L at some time, T, where T is 5. So L at 5 days, we can describe that mathematically as L0 minus BOD at some time T, where T is 5, right? So that's kind of the formal way to say it, which is quite obvious when I say this is 21 milligrams per liter that we just calculated minus the 18 that we calculated, gives us 3 milligrams per liter remaining as our answer. So very, very plain and obvious written that way. But now we go to estimate the reaction rate constant for this BOD removal as K in per day units. So here's where we get into a little bit fancier math. We can say, find our equation that BOD at some time T can be given by L0 times 1 minus E to the minus K T. And rearrange that and solve for the K. And so this will be getting us a little closer to kind of reaction kinetic sort of thing. So T is 5 days. Our BOD at time T, at 5, that was our 18 milligrams BOD per liter. And our L0 is 21. milligrams BOD per liter. Okay, so with that, we can rearrange a bit. I'm going to do that before I put in the numbers here. 1 minus e to the k negative kt. If we just divide both sides by L naught, we can set that on the left side. We have BOD over L naught. We can isolate the e, multiply both sides by -1. That'll get us, just move it over here. So e to the minus kt equals 1 minus BOD t divided by L naught. Then we can take the natural log of both sides. That'll get rid of the e, so we're left with minus kt equals natural log of this stuff. 1 minus BOD over L naught. Okay, divide everything by negative time, and we'll be set. So I'll just go ahead and skip ahead and say k then should be 0.389 per day. All right. Any questions on that? Okay. All right, next, problem 4. I think this is our last one, but it's got several parts. Suppose the only source of BOD in a river is untreated wastes that are being discharged from a from a food processing plant. The resulting oxygen sag curve has a minimum value, DO, somewhere downstream equal to 3 milligrams per liter, as seen in this figure. Just below the discharge point, the DO of the stream is equal to the saturation value of 10 milligrams per liter. Part A says, by what percent should the BOD of the wastes be reduced to assure a healthy stream with at least 5 milligrams per liter of BOD everywhere? So basically, we want to redraw the sag curve, find out what we need to do to achieve a new minimum at 5, so that wherever that minimum is occurring, it only goes to 5. That's a very bad curve, so I'm just going to leave it there. Okay. So, and then the question continues, would a primary treatment plant be sufficient to achieve this reduction? All right, and a primary treatment plant, it removes a little bit of wastewater, a little bit of the BOD. Sometimes it could maybe do even up to like 40 or 50%, probably usually not quite so much. Probably more like the 20 to 30% range. It's just basically getting out the major particles that can be removed. And if that's enough based on what's in the water, what's causing the oxygen demanding stuff, maybe. So if we only need like a 5 or 10% change here, it probably can. All right, so this is an interesting one. And solve the entire problem and then come back to answer this one, but as we'll see, there is a bit of a shortcut. We don't have to do that. We just have to take a look at the equations needed. So this is fairly involved, and I don't think I would give you one like this for part A on the exam, but I want to show you kind of what's happening with it and what we're doing. So first of all, we can take a look at Kr, the reaeration rate constant is given. Sometimes we might need to solve for it based on the stream, but we're given it this time. And Kd, and note that they are not equal, right? So Kr is not Kd, that means we're not dealing with a division by 0, and we are set to use the standard equation where we have the deficit is equal to Kd L naught, L naught, divided by Kr minus Kd, times this term here, e to the minus kdt, minus e to the negative krt. All that plus the initial deficit, which turns out to be 0, times e to the minus krt. So this equation gets simplified here because that goes to 0. And that happens because we were told just below the discharge point, the du of the stream is equal to the saturation value. So the initial deficit equals 0. Okay, so that's coming from there, and that we can also see that right here, that the saturation value line drawn here, we're starting at that point. Okay, so practically speaking, that doesn't normally happen. Normally we have a little bit, but again, practically maybe it's close enough in many cases. Okay. Okay, so then this equation simplifies a bit so that we have just this first term times what's in these the parentheses, right? And if we stop and think about it for a moment, that means that there's going to be a direct relationship between D and L naught. So they're directly proportional. It's slipping my mind. There's a symbol we can use to say it's directly proportional. Is it 3? What's that symbol?
It's infinity, but you don't finish it.
Like this guy? Yeah. So okay. So D then is directly proportional to alpha, or excuse me, is directly proportional to L naught because of that little simplification that we were able to find. So that means it's quite handy if we know that and this equation, by the way, this is the deficit at some time, so we can say the deficit at however much time it takes to get to our minimum. We can use the same equation for the deficit at that minimum, right? So if we keep all of that the same, some arbitrary time, this direct proportionality is going to stay the same. So that means we can actually say that this is funny. Now I see it written on my notes, the little alpha. It's like I must have done the same thing last time. Okay, so that what we can say then is our initial deficit and our initial total BOD that we have to deal with, we'll call that L naught 7. So the condition where we reached a deficit of 7, we can compare that to the initial condition that reaches us a deficit of 5 milligrams per liter, or excuse me, that reaches a worst case deficit of that. And if we just simply describe that and leave out everything else in the equation but the 5 and the 7, we can relate them by just simply dividing one by the other, saying L naught 7. Well, I'm gonna flip that. I'll say 5 over L naught 7 is just 5/7, right? It's very simply stated that way. The amount of BOD that can be remaining, or the difference here, is described by 5/7. So if our new deficit has to be smaller than the bad case, the 7 case, it has to be that ratio. It's as simple as that. The wastewater needs to be reduced by 5/7, or reduced to 5/7 of the original, because of that proportionality. So that means that if we write this out as a fraction, that's 0.714. So we could say that's 71.4% remaining. So if we have 71.4% of this ultimate BOD that can be remaining, that means we have to remove about 28%, 28.6%. BOD. Okay. So it's a very kind of simple way of approaching this problem. I say simple. it took some, it's not simple to notice that we have this d naught go to 0, and that simplifies everything to the this proportionality. But given all that, then it's kind of simple right there. But again, I'm not really looking for you to be able to find that simplification necessarily. You could have also just solved the problem and found the numbers, which would have taken you a lot further down the questions. Like, you probably would have had to solve most of the whole problem to get there, and then made a comparison. That would be totally fine, and you should get the same number, right? If you had done it that way. Okay, at any rate, this is the answer. And so primary treatment, I'm a little on the fence for that part of the question. I'd have to go look back up exactly what we might expect. I'm going to say probably not sufficient. Something is telling me that it's up to maybe 50%, but I think it's not usually quite that much. Okay. Again, it probably depends on the type of wastewater, so it might be worth a shot at seeing if that can be done. All right. Moving on, part B says if the stream flows 60 miles per day, has these rate coefficients that we saw in the drawing, how far downstream in miles would the lowest DO occur? So we're looking for that value, the XC, that critical point, which means we really need to find the critical time, right? And then we can use the speed, velocity to solve for time, or solve for distance. Okay, and we have an equation for that. This is, at this point, pretty much a matter of plugging in the numbers and chugging right along. So KR, 1 over KR minus KD. Here is the equation times natural log of KR over KD. Here's that one that I told you to integrate, right? And fortunately, we didn't feel the need to do that. In this part of the equation, we have D naught again multiplied by, I'll go ahead and write it out, but this all goes to 0. KR minus KD over KD times L naught. Since this is 0, our calculations become a little bit simpler, and TC here comes out to be 2.31 days. Everything that we're feeding into this, I think, is already in days, so that works out nicely. The per day units for the rate constants. So we get that value, and then from there, we simply need to multiply that by 60 miles per day. And that'll give us to 138.6 miles for our answer. Okay. So again, if there was some sort of confusion, it's probably on the deficit, and recognizing that was 0 for that part. All right. Any issues or questions there? Good. All right. Part C then says, what is the ultimate BOD L naught in milligrams per liter of the mixture of river and waste just downstream of the discharge point that would cause a minimum DO to be 5 milligrams per liter? So this is kind of bringing us back to part A. Like I said, what you'd find is if you got to this point and you had taken the brute force method to solve it in part A, to solve exactly for this and for exactly this for the 7 case, then you would have realized, oh, I already did this by the time you get here. So it's really no problem if you did it that way. And so here would be the solution. So the L naught under the 5 deficit case is what we're looking for. So our deficit is 5 milligrams per liter. And we can set that equal to the equation that we had already discussed, right? KD times L naught. and we will solve for the L naught there over Kr minus Kd, all that times the e to the minus kdt minus e to the minus krt, all that plus the initial deficit term, which is going to 0, and we rearrange and solve for L naught. Right, so basically we're just going to divide everything by the rest of this. So isolate the L naught. Okay, we'll save all that algebra. It's pretty straightforward. And once we solve it, this should become 31.75 milligrams per liter. Okay. Okay on that? All right, so the last part says sketch the oxygen sag curve before and after treatment, labeling critical points and the DO minimum value. So I kind of already did this just right out of the gate in some way, but we'll go ahead and write this a little more explicitly and put a sag curve, like the critical time point here is 2.31 days. That corresponds to a distance, if we were to write it that way, as 138.6 miles. And it doesn't actually matter what our L naught was. The critical point is going to happen at the same time and distance. So it doesn't matter how much we're starting with. The proportionality makes it so that they dip to the lowest point at the same time or distance regardless. And that'll be apparent if we take a look back at this equation and we see that at least in this formulation, where the initial deficit was 0, the L naught doesn't matter for finding time. Now, it certainly could matter if the initial deficit was not 0, right? So maybe we'd have to do a little bit more to solve for that. But in this scenario, thankfully, these are going to be the minimum points regardless. So if we have that saturation point, and that was 10 milligrams per liter, this is our, we could write, I guess, the DO here, so that would be 10. And the difference between that and our point would be the deficit. So a deficit of 5 would be right in the middle. A deficit of 7 would give us a value of 3 milligrams of oxygen remaining per liter. So our bad case scenario goes down to the 3 mark. We'll give that a nice red. So looking something like that, where that's our minimum point. And then the better case only goes down to 5 milligrams per liter. Something like that. Okay, so pretty straightforward. Just want you to label it and also to recognize that the time and the distance is the same for both scenarios, given that L naught had nothing to do with it when solved with a 0 initial deficit. All right, that's all I've got for you for the semester. So any other questions or concerns, comments? Yeah. Yes. Yeah, so in total, so the exam is cumulative, but partly, right? So it'll be 50% cumulative in the sense that you can expect about 1 problem from exam 1 material. About 1 problem from exam 2. and about 2, and I'm not promising it's exactly those numbers, but proportionately 25% from exam 1, 25% from exam 2, and 50% from everything after that. And I'll just say that's wastewater and BOD stuff. So approximately like that. You know, if the previous exams took you 1 hour, maybe this will take you 1 hour and 15 minutes, something like that. If you spent the full time last time, maybe you'll spend the full time, hopefully not this time. You know, as you noticed, the second exam, I kind of messed it up and made it difficult, and so the grades came out a lot more lenient. So I'm not planning to do that. I don't want to mess it up for you. I want it to be challenging enough so I can see that some of you have learned this stuff and mastered it better than others, and I want to be able to see that difference, right? That's kind of the point. I'm trying to measure how much you've learned, right? So that's my goal. All right. So you'll see some updates on grades as I get them with the participation and stuff. Like I said, if you've been following the scoring, like I don't know if I talked much about this, but if let's say you took one of the quizzes and you got nothing right, you're still getting 70 to 80% of the credit for having participated in it. So that's meant to be like, hey, are you engaging with the content? You get a little extra for doing so, right? And a tiny motivating factor for trying to actually get it right. So, okay. All right. With that, good luck on your finals, and thanks for the semester.